in addition to my presentation, Natalie Shishov and Karam Elabd are two trainees in my laboratory who will be presenting their work, which is a bit of a progress report, just updating you on their efforts. And as Dorina mentioned, the webinar will be available on YouTube, so we're going to kind of rely on that to move, at least I will move quite quickly through some slides, but really look forward to the Q&A afterwards. And all right, so let's start talking about the cost of falls in Canada. And while falls are important for other reasons, one of the main problems, of course, is the injuries that are caused by falls. Hip fractures are probably the most important injury in terms of number, cost, and influence on quality of life. There's about 30,000 annual hip fractures in Canada, and 25% of patients will die within 1 year. 50% will lose independence. The other type of injury that's really of growing concern is traumatic brain injury. There are about 20,000 cases annually in Canada of traumatic brain injury in older adults. 80% are caused by falls. And there has been a 2- to 3-fold increase in the age-adjusted rate of traumatic brain injury over the past decade. Now, preventing falls and injuries is a challenging task because, falls, the etiology depends on this interaction between these different domains that are shown in this slide: physiological, behavioral, and environmental. So someone may be falling because of behavioral factors related to risk-taking. They may be falling because of environmental factors, hazards in the home or environment, or because of physiological factors like impaired gait and balance. But more often, and as you'll see through the research that we'll present, it's really a combination of these factors, and that's the challenge that makes falls resistant to intervention. And we'll be talking, a lot about that whole challenge. I want to start by having you think about the future. So I say here, a dystopian future without injury prevention. And imagine a future which really is not so far-fetched, a future where all disease has been cured. Humans can then theoretically live forever unless they die from an injury. And we can imagine that often that injury will be related to a fall. So in this dystopia, people become fearful of falling, fearful of injury in general, restricting their activity levels. And how might we prevent this kind of dystopia? We can think about an example of, in cardiology, the pacemaker was an intervention that for the past 50 years has really revolutionized the treatment of any type of arrhythmia by allowing, return to a normal sinus rhythm. And, this is kind of what we would love to be able to come up with in terms of falls. Like, is there a single robust solution to the problem of falls analogous to the pacemaker? Well, we can think about so-called, I label them here as sci-fi solutions, but I think you'll agree that many of these are solutions that people are working on right now. We could think about pharmaceuticals or other approaches to enhance resistance of tissue to trauma. So regardless of what kind of impact, there is no injury. We can think about tissue engineering approaches to regenerating damaged tissue and organ. And imagine that probably the biggest challenge will be the ability to regenerate damaged brain tissue. We can think about technologies like exoskeletons or functional electrical stimulation that prevent us from ever losing balance, so there are no falls. We can imagine wearable protective gear that is somehow as comfortable and non-obvious as your favorite shirt, looks great, but it is so effective that it prevents any kind of injury from occurring in the event of a fall. And lastly, I list modifications to the built environment to make it completely safe for falling. So again, you can imagine, you can sort of see like, okay, we're making some progress in each of these areas, and I'll return to some examples throughout the presentation. Now, I'm going to tell you quite a bit about our work, and Natalie and Karen will focus on their work, but I'm also going to kind of step back and give you an overview of technology, specifically focusing on information and communication technology, or ICT, and the different types that are available in the area of falls. So we can think that like a lot of these involve a medical support system that communicates either with smart home sensors or wearable sensors. And these sensors may be for applications like fall detection, determining whether someone's in bed or has left the bed, measuring gait and balance or metabolic energy, physiological sensors for heart rate. We can also think about growing use of things like healthcare robots that may have a role in fall management, home delivery of exercise programs. And we'll talk about that. That I think is a very promising area for ICT. And we'll talk a little bit about active inflatable protective clothing. But returning to the wearable sensors and the smart home sensors, there are barriers here. And one we'll talk about is the challenge of accurately detecting a fall. There's some barriers that are specific to wearable sensors, like battery life, and ambient sensors, like the need for multiple cameras to visualize a fall. Now, a really important area that I just really have this one slide on, but it's important for us to think about is, the effectiveness of any technology depends on, what we might think about as, let's say, its biomechanical effectiveness, like how well does it actually work in, doing the job, but then, like detecting falls. But then the other thing is user acceptance or compliance with that technology. And really, we've listed some things here that have been identified that are pretty general in terms of adoption of older adults' attitudes and, the barriers to adopting technology, whether they're intrinsic or extrinsic. But the point here really is that more work is required, specifically in the area of ICT for falls management, in order to understand, like, what are the barriers and facilitators to use of these technologies by older adults. Now, let's talk briefly about fall detection. So this is technology that would automatically detect that an older adult has experienced a fall. And you may be aware that there is a growing number of companies and growing number of research groups who are directing their efforts towards development of these systems. And you see images of some of the systems that are either wristwatch-based or pendant-based. And a recent report, valued the market currently at about 360 million and predicted that it will increase to about 500 million by 2022. I've listed some of the major players. And you can go to this website that you may have encountered. I've encountered for other things, but I happen to find that, they have a review of fall detection sensors on this top 10 reviews website. And you can see that here are various devices that are ranked. Some of them you may recognize. The one on the far right, the Philips Lifeline, is no doubt the most common device that's currently on the market. And on this website, they even have scores for fall detection. I don't know if you can see my cursor, but here's the score was 75% for fall detection, goes up to 80, down to 50 for the Philips. So they actually conducted some of their own tests on how often the device really detected a fall. Doesn't look very high, does it? And we'll talk about why, but just before that, part of the, you know, when you look at the overall market, we talk about how it's growing and everything, but, and it seems like there's a lot of devices out there, but if you look at the technology readiness level of this sort of technology, it's low to moderate. On a 9-point scale, it's between 4 and 5, which means that the technology is at the research and not the prototype stage. It's been validated in the laboratory environment, or in some cases in a relevant real world environment. But there's a lot more work to be done. Now let's briefly talk about the problem of, you know, fall detection and how well you can really do. Like, why, you know, in those tests were they seeing 75%, 80%, 50%? Well, if we look at the work that we've done in the ability of a 3-sensor system to accurately classify different events, we have, let's look at the table. We see that the sensitivity and specificity of this 3-sensor system for distinguishing activity, like is a person walking, are they lying, are they transferring, that's really high. It's also pretty good for telling you, like, if someone fell, what was the cause of the fall? Was it a slip or a trip or some other thing? And the crucial thing for those two things is it's really not that horrible if it gets it wrong, you know, 1 or 2 times out of 100. But if we think about fall detection, it becomes more crucial. We want a fall detection system that identifies every fall, meaning it has 100% sensitivity, and we want a system to identify, to not have any false positives. So we don't want that alarm to go off if a fall actually hasn't occurred. That means 100% specificity. The problem is we can't get both. We don't have the algorithms currently in order to get both. So we sort of have to threshold it one way or another. And if we look more specifically, the system is evaluating every 5 seconds whether a fall has occurred. It's running the algorithm saying, is it a fall or no fall? So every 5 seconds, what that means is there's over 17,000 evaluations made every day. So really you need 100% specificity to have no false positives, like really so close to 100% specificity to avoid false positives and a kind of cry wolf phenomena. So, you know, we can go to 100% specificity as shown in the last, I lost my cursor here. The last, here we are, last row in this table, but the cost is we're going to miss 1 out of 5 falls. And not surprisingly, a recent clinical study done by a group in Boston found that the Philips Lifeline had even worse performance than we just went through. Those numbers that I just reviewed, about 80% sensitivity for 100% specificity, that's based on lab studies. In real world, what this group found was that sensitivity was about 20%. It only found 1 out of 5 real-life falls, and about 87% of the alarms were actually false positives. So there's a lot of work left to be done. Now let's talk about fall prediction. And if you think fall detection is hard, fall prediction, we're even at an earlier stage with this. Let's look at it for a moment about, you know, clinical predictors of falls. How well can a standard measure of mobility and balance, for example, the timed up and go, distinguish between fallers and non-fallers? Well, really, it doesn't do a very good job. A meta-analysis found that, you know, there was a small difference of 0.6 seconds on this test, which normally takes about 10 seconds for an older adult to complete. There was only 0.6 seconds difference for older adults in the community, a higher difference for those in institutional settings, but the overall conclusion from this meta-analysis is that, you know, didn't support, the analysis does not support the TUG to classify people accurately into fallers or non-fallers. In our own work, we've looked at what are the predictors of risk for falls in older adults after they're admitted into long-term care. And by far the strongest determinant is fall history. Also important are measures of unsteady gait and use of specific medications. But really, fall history, when you think about it, it's something that encompasses all the other variables that are really hard to measure, but might go back to like what we were talking about, like behavioral, like risk-taking behaviors, or well, on the other hand, sedentary behaviors, environmental factors, and so on. But if you look, area under the curve here is about 0.8. So we're not doing too great, really, in predicting who will fall. Now, there are promising data emerging. For example, Marjorie Skubik is a researcher at University of Missouri who's got 10 years of Connect data from 54 independent living apartments. And this Connect, and I'll play the video here, this is what it's collecting. It's nice because it's sort of anonymized. It's just, you know, the silhouette of the individual, but they're able to get stride length and walking speed information. And they found that a decline of 5 centimeters per second or more in walking speed over 1 week period predicted risk for falls in the upcoming 3 weeks. With 86% probability, individuals who had that decline were 4 times more likely to fall than those who didn't. So again, it's preliminary, but it's giving you an idea of the kind of technologies that are emerging that have promise in this area. Now, preventing falls. Here we see some older adults at a local park in Vancouver who are engaging in Tai Chi. And again, let's look at the clinical evidence. What do we know about interventions to prevent falls in older adults? And starting with community, so we're looking here at Cochrane reviews, which again are meta-analyses of many studies. We start by looking at community-dwelling older adults. We know that exercise is effective in reducing the rates of falls in that population. The meta-analysis found 37% reduction for Tai Chi. We also know that individuals who are taking specific medications like psychotropics, withdrawal from those medications can have a substantial effect in reducing falls. In community-dwelling older adults, we don't have a lot of evidence for home safety interventions as being effective, although I'll present one example that has been effective, or for vitamin D. On the other hand, if you look at the community of older adults who live in long-term care, who of course tend to be much frailer, there is lack of support for exercise interventions. And the question is just, you know, do we not have the right types of exercise? Are we not measuring the effect properly? If we get people exercising, and this is something that we continually talk about, we get them moving more, are they you know, does that offset the reduced risk for falls per unit of activity? And that's an important question. With older adults in long-term care, vitamin D has been shown to be effective, as well as multifactorial interventions. So here's that exception, was a study that was done in the community and found that a $560 New Zealand intervention, I remember converting that as about the same, I think, in Canadian dollars, that it reduced medically treated fall-related injuries in the home, you know, occurring in the home by 26%. And this was found to be, you know, there was a pretty strong argument for the cost effectiveness of this. So I don't think, you know, we can't ignore the value and really the ease of environmental modifications to prevent falls. This is an exciting result from a group in Israel that, you know, I mentioned that ICT for home delivery of exercise, I think it's a really promising area. And here's a study that found that treadmill training in and itself, in this population of older adults who are at high risk for falls, that it actually didn't reduce falls. You see the blue line, it actually shows a slope towards reduction, but it wasn't significant. On the other hand, when you added to that same treadmill training, based a virtual reality program that required the participants to negotiate hazards like, walking over logs and across puddles that come up in the road and so on, that had a much stronger effect in reducing falls. So this is where we can start to think about, okay, virtual reality, it's growing, it's can be implemented in the house, a coach can be hooked up to an individual in a house to deliver via ICT an effective exercise-based training program. We mentioned in our Sci-fi solutions exoskeletons, and we need to be clear that I think we're far away from having a solution in that regard. But of course, people are working on it, and the more people work on it, the more promising the solutions may appear to be. Here is an example of a study that found that an exoskeleton that actuated at the hip in assisting stepping was able to enhance balance recovery. We don't know if it would actually prevent falls in older adults, but it's an interesting idea. Now, let me transition to talk more about some of the work that we're doing with regard to real-life laboratories for falls and injuries. And Dorina kind of provided an overview of some of the work we're doing, both on video capture, wearable sensors. And you'll see like the work we're doing in that area really has a lot to do with problem finding, like using the videos to ask like, how did this fall occur? Why did this fall occur? How did this fall lead to head impact? How did this fall lead to hip fracture? And then another part of our work is on problem solving through interventions like wearable hip protectors and compliant flooring. So in terms of the video, we've been doing this now for 10 years, and we have partnered with 2 long-term care facilities to have 270 cameras in common areas, and we have now collected 2,400 falls experienced by over 650 residents. For a lot of the individuals, we have consent to access the medical records and separate consent to share the videos for education. And I'll come back to that. But just to note that all the images and videos that we're going to show of older adults falling, we have that consent to use the images for education. So here's an example, and I don't have time to show many, but here's an example of a fall due to a trip. And you can see that an environmental hazard, the individual's walker was involved. So that's one type of fall that we see. Here's another type of fall that is a misstep. And it doesn't involve any specific environmental hazard, although you see the woman is in sort of an emotional state where she's a bit worked up, and this may have contributed to the fall. And that fall is difficult to watch for many reasons, including the fact that it resulted in head impact. So we have 2,400 videos of falls in older adults, and many we have multiple views from different cameras. But how do we get data from these videos? So a lot of our work is related to the sort of video analytics, and we've developed a questionnaire that probes through a structured process of questions with multiple response categories, features of the initiation, descent, and impact stage of the fall. So I'll show you a little bit of results from, for example, with the initiation stage, we've looked at, what was the person doing at the time of the fall, the activity, how did they lose their balance? With the impact stage, we're interested in things like, what body parts impacted the ground, and I'll show you a little bit of detail on that as well. We're also interested in, balance recovery responses and fall direction and changes in direction and so on. But here's, some data looking at, sort of how the falls occur. Like, what was the person doing, the activity at the time of the fall, shown on the vertical, versus like their, the cause of imbalance. And the point that I want to make here is that most falls in this setting, in this population in long-term care, are not due to slips and trips. Trips make up 14% of all falls, shown on the far right. Slips only 1%, but nearly half of all falls are from incorrect weight shifting. For those, so there's things like excessive sway or failure to, achieve a state of balance during rising or descending. Loss of support is also common. The other point that I want to make here is that, walking is, if you're only focusing on falls during walking, which are shown in the green, then you're missing a lot. In this population, falls are just as common during standing, shown in the blue, and in transferring. Surprisingly, falls are more common during sitting down than getting up. So, when you're talking about sort of problem finding, I think these data are really crucial. When we talk about impact sites, here are some graphics that show on the left side, what are the impact sites that people contact during a fall. And we see like 93% of falls involve impact to the pelvis, 67% hand, 33% head, which is alarming. But even more alarming is if we look at the sites of injury, 35% of all injuries are to the head. Only 1% of injuries are to the pelvis. So clearly there are sites that are safe to impact and sites that are less safe to impact in terms of risk for injury. In terms of head injury, or head impact, I should say, well, forward falls created the greatest risk. Nearly 50% of forward falls caused head impact. Backward falls were much more common. So the largest number of head impacts were to the back of the head. 13% of all falls caused impact to the back of the head. All right, I just have a couple more slides quickly before I turn things over, just to mention that we are also doing work on hip fractures and hip protection against hip fractures through wearable hip protectors. We've developed and are really excited about a product for the acute care environment that is basically a padded bandage that works just as well as existing hip protectors and gets rid of the garment, and we hope will be much more, have much more higher compliance in that environment than traditional garment-based hip protectors. And here's another thing we're working on with an Israeli company, which is the high end of hip protectors, an inflatable hip protector. So you see, we're really working on both ends, the low cost and the high cost. And finally, we are just wrapping up a clinical trial of compliant flooring for, which we conducted in one of our partner long-term care sites. It's a 4-year trial, which has its outcomes: falls, injuries from falls, and serious injuries from falls. And we're very excited about this. Okay, so lastly, I thought this was the last slide, but lastly, I want to briefly mention and ask you to really consider work that we are going to be doing in the future about sharing videos. Think about how the videos, you saw just 2 examples, you'll see some more from Natalie and Carol. Think about how they may be valuable to you in your own research. And we are making it happen, that we're going to be sharing it starting in September, over 100 videos on this NYU-based network Databerry. It provides a platform for research, teaching, and learning. And keep in touch with our website. Go to Databerry to take a look and sign up. You need to sign up to Databerry and only to access the videos, but we're very excited about this and encourage you to think about how that can be valuable for you. Okay, so I will now turn it over to Natalie.
Hello, everyone. I'm a student in the lab, and today I will talk about an analysis of the association between leg raise and head impact during backward falls in older adults in long-term care. This study emerged as part of an initiative to identify the factors that separate falls that do and do not result in head impact during backward falls. So in older adults, fall cause up to 80% of traumatic brain injuries, which are associated with substantial decline in quality of life, mortality, and economic costs. In a previous study done in our lab, it was found that 37%, 1 of 3 older adults who falls in long-term care will impact their head. Backward falls were also reported to create, most of this head impacts occurred during backward falls, which were also reported to create the greatest risk for traumatic brain injury. If differentiating initial fall direction and backward landing configuration, which might be different due to rotation during the fall, 34% of head impacts occurred in backward falls with initial backward fall direction, and 42% of head impacts occurred with backward landing configuration. In backward falls in general, impact to the pelvis tends to occur before impact to the torso and head, which is also what we see in the database of the real-life video falls in our lab. When initially observing the backward falls in older adults in long-term care, we noticed that in some falls, there is a leg raise that occurs after pelvis impact. And a suggested mechanism that might explain this is conservation of angular momentum. So in landings in which the pelvis impacts the ground before the torso and head, angular momentum consideration suggests that the probability for head impact might be reduced by raising the legs after pelvis impact. So to visualize this, if we look on the figure, raising the legs after pelvis impact will result in increase in the upward angular velocity of the legs, of the left component of the conservation of angular momentum equation. And because the summation of the upward velocity of the legs and the downward velocity of the torso and head is constant, increase in the velocity of the legs will result in decrease in the angular velocity of the torso and head. This will slow torso descent, and by so might reduce the risk for head impact and injury. Therefore, in this study, we analyzed real-life video footages of falls of older adults in long-term care to test the hypothesis that leg raise after pelvis impact associates with decreased risk for head impact in backward falls. From a database of 2,321 real-life video footages of falls of older adults in long-term care, we identified 800 falls with initial backward fall direction. From these, we identified 215 falls that included impact to both the pelvis and torso on the ground, and also had backward landing configuration, meaning that we looked on strictly backward falls. 85 of these falls resulted in head impact, and in 130 did not involve head impact. We then analyzed each fall to extract information regarding 2 fall characteristics. The first is the angle of the torso with respect to the horizontal plane at the moment of pelvis impact, classified as closer to vertical versus closer to horizontal torso angle. And the second is whether there was yes or no, or an observable raising of the legs off the ground after pelvis impact. So these are examples for the fall characteristics we observed. On the left, we see a video of a fall in which head impact was avoided. So we first saw it in natural speed and then in slow motion. And we classified this fall as having a closer to vertical torso angle at the moment of pelvis impact and having leg raise. And in the bottom, we can see snapshots of the moment of pelvis impact where we identified the angle. And on the right, we see a snapshot of the leg raise. Now on the right, we see a video of a fall that did involve head impact, which we classified as having a closer to horizontal torso angle and having no leg raise. And again, in the bottom, we can see the moment of pelvis impact, and we can see that there was no noticeable leg raise on the figure on the right. The reason that I chose this example is because they're representative of the trends that we found. So what we found is that of the 85 falls that involved head impact, 41 falls had leg raise. Of the 130 falls that did not result in head impact, 107 involved leg raise. Of the 148 falls that involved leg raise, 41 resulted in head impact, and of the 67 falls that did not involve leg raise, 44 resulted in head impact. So if we look on the mosaic plot on the right, most of those who raised their legs avoided head impact, whereas most of those who did not raise their legs did impact their head. And based on a statistical analysis based on chi-square, we found a significant difference in the frequency of head impact between falls with and without leg raise, with a 5-fold higher odds for head impact in falls that did not involve leg raise. Additionally, in 179 of the total of 215 falls, we were able to detect the angle of the torso at the moment of pelvis impact. And we found a significant difference in the frequency of leg raise between falls with a closer to vertical and closer to horizontal torso angle. So of the 96 falls that had a closer to vertical angle, 78 falls included leg raise, whereas of the 83 falls with a closer to horizontal angle, only 51 falls included leg raise, meaning that individuals whose trunk angle was closer to the vertical at pelvis impact were more likely to raise their legs. Additional thing to note is that hand or hands impact during the fall were not found to be protective against head impact during backward falls. Hand impact was observed in 129 of the falls, and there is no association between hands and head impact, which aligns with previous study done in the lab that also did not find an association between hand and head's impact when analyzing all fall directions together. So to summarize, our results suggest that leg raise is a commonly observed strategy during backward falls in older adults in long-term care. Leg raise reduced the odds for head impact. The apparent mechanism for leg raise is conservation of angular momentum. It exploits angular momentum principles to slow torso descent and avoid head impact. Leg raise was more common in falls where trunk was closer to upright than horizontal at pelvis impact, so when the individual landed at a more sitting position. Hands impact was not found protective for head impact during backward falls. And we suggest that improved understanding is required on how leg raise depends on muscle strength and flexibility and on passive dynamics versus active neuromuscular responses, because this understanding can advance possible training. For example, if it is found that leg raise depends on certain pattern and intensity of active muscle responses, then perhaps leg raise is something that can be integrated into trainings to protect the head, for example, by strengthening these muscles or using instructions to work on activating them during backward falls. I have a slide with reference if someone wants to read some more into it. Thank you for listening. And now Kerem will talk about his work.
Okay, so hello everyone. Thanks, Natalie. I wanted to thank you all for being here, and I wanted to thank Steve for giving me the opportunity to highlight my research. My name is Kerem. I'm a graduate student in the lab, and my project's mainly focused on designing and implementing this articulated falling dummy that we're designing to simulate impact dynamics of the human body throughout a fall. And the purpose of this is to sort of reliably test and evaluate the protective gear like helmets, compliant flooring, hip protectors, and so on. Now, I'm still pretty early in this, but in this presentation, I'm just going to sort of highlight the motivation and provide you some of the progress that I've done so far. So Natalie will have already covered a lot of the relevant background, but I wanted to orient us again by briefly mentioning all of the main takeaway points. As you may have already pieced together, falls are a major cause of injuries and morbidities, and traumatic brain injuries are amongst the most common and most dangerous. And it turns out that older adults are at a much higher risk of sustaining a fall-related head injury, and that though head injuries and head impacts are more common in forward falls, backward falls are much more likely to result in moderate to severe TBI. So head injury prevention products need to be designed and evaluated under realistic impact conditions. Now, there are protective products that would help reduce the risk for head injury from falls, devices like compliant flooring and protective headgear, so helmets and hat liners mainly. But I've been looking at the mechanical testing standards and systems that are used to evaluate the protective value, and we found that these drop towers that you see on the right here, I'll show you a video momentarily, we found that they have some non-trivial limitations because they don't really account for the complex behavior associated with fall. And so this video would be a good example of helmet testing. This particular test was done at the Bell Helmets Test Lab. And there's a head form inside of the helmet, which would be fitted with a 1 or 3 dimensional accelerometer system. As you can see, it's a purely one-dimensional momentum exchange, and linear acceleration is kind of the primary outcome, where rotational acceleration is kept at a minimum. And in response to this, we've decided to build an instrumented falling dummy that would help us better simulate those important fall characteristics. So here we see a really early stage, or even a first iteration of our dummy. As you can see, it's got a rigid and curved back segment and some very rough mass distribution around the pelvis and legs. And so we're designing our dummy to mimic the falling behavior of older adults during backward falls from the point of pelvis impact. And we've chosen to initiate the fall from the point of pelvis impact because you could probably imagine that almost every backward fall involves pelvis impact unless we were to fall over a chair or something like that. And so it looked like a reasonable place to base our simulation off of. But that means that the torso design is going to be especially important to further examine the translation of the forces leading up to head impact. So with emphasis on the back's profile and its dynamics during the fall. So for characterizing the shape and the geometry of the back for older adults, we're going to be using something called a vac pack, which first and foremost, it's a surgical positioning device or tool. You can think of a vac pack as kind of a beanbag that allows us to vacuum all the air out from it. And effectively by doing that, it allows us to retain the shape or the physical features of the body positioned on top of it. So we figured that for our purposes, we would conduct a study using this vac pack to determine a sort of average shape and size for an older adult's back. And we'll do this by digitizing the important surface markers that are imprinted on it by means of a 3D digitization pen that we have in the lab. Now, the backpack would help us design the profile of the dummy, but to determine the dynamics of the back during a fall, we've resorted to using video analysis. So Steve's already mentioned that our lab does quite a bit of video collection. And so I'm searching for a number of random representative backward fall videos and manually tracking the surface anatomical features representing the faller. And I'm especially interested in the behavior of the back throughout the fall. So you'll see here that I've selected 6 points on the back, creating a 5-segment back model that you can see in green. On the right, I'll show you a short video where we can see the 2D traces of the points being tracked for one of the participants in the lab. And as you can see, I've also tracked the head, pelvis, knees, and ankles to provide some valuable information on the impact kinematics. So what you see here is the fall trajectory plotted in MATLAB. The thinner dashed lines outline each frame of the trajectory throughout the fall. So basically that's the time-varying shape and position of the back. The diamond at the top represents the uppermost part of the back that was digitized. So that would be approximately the C7-T1 junction on the spine. And I programmed it so that it would change colors at the point of hip impact. And the thicker line shows the shape and position of the back at the end of the fall. The thicker line in black and red. So this is an example of the digitization process for real-life fall video from surveillance footage of an older adult falling on the right-hand side, and the 5-segment model is being run on the left panel. And as we mentioned before, the back segments will change color once hip impact occurs. Hopefully you've spotted that. And this is our falling dummy in action. As you can see, the back segment's very stiff and it sort of pendulums after head impact. I haven't come up with a very systematic or repeatable way of applying the force to initiate the fall, but we're working on some ideas. But in the meantime, I've been using this padded staff and sort of trying to manually apply a one-dimensional push and using motion capture to categorically sort the velocity I'm imparting the dummy with. This would be the fall trajectory for the dummy, so quite different from that of the adults. And to conclude, I wanted to show you this kind of superficial visual comparison between the falling trajectories of different fallers. And the reason I pulled this up is to show you that by introducing some mathematical modeling to characterize the fall traces of each point on the back, or maybe fitting a time-varying shape of the back into a polynomial equation, we would have a metric that would allow us to check for a best fit between the dummy's falling behavior and that of an older adults. And that would potentially help us characterize age differences as well in falling behavior between older and younger adults. So our next step would be modifying the dummy with the aim of improving that match and eventually using the dummy to evaluate the protective value of injury prevention technology. I've also included some references if you guys want to do some more reading. It should be available in video. And that's all for me. So thank you.
All right, great. Thank you. Sorry, Natalie and Karen. And Dorina, I think I'll pass it back to you now.
Great, thank you. So this is a slide just as a reminder of what AgeWell is. I think usually we throw this one at the beginning, but just again, if you want to know more about AgeWell, visit the agewell-nc.ca website, and I'll tell you just very quickly about our upcoming webinars as you think of any other questions that you might have. We've got about 3 or 4 lined up for our presenters. Could you go to the next slide, Steve? One more.
I think that was...
Oh, okay, that was it. There was another part. That's okay. Just so you know, our next webinar is on Tuesday, August 21st at 2 p.m. It's on training the entrepreneurs of tomorrow. You can find information on it on our website. I'm just putting the links into the chat box now. The first link will have the information, and the second link is the registration link. In terms of questions, the first one was from Maria asking if there are adhesive hip protectors available in Canada.
Are there hip protectors available in Canada? Or...
Yeah, the adhesive type. I'm guessing it's like, are they available on the market? Perhaps you could talk about where the ones that you're working on are at. Like, can I go and buy one? I'm guessing it could be a caregiver or older adult in the audience.
Unfortunately, the answer is no. I hope that if that the answer will become yes in 6 months from now. We are working to deliver it to acute care environments, sorry, in Fraser Health, so hospitals in Fraser Health, where we'll be doing a clinical trial of patient compliance in, using the stick-on versus the normal garment. So we're very close to commercialization and delivery, but yeah, it'll be about another 6 months to a year before, best case, before it's actually on the market.
Great, thank you. The next question is for Natalie. So the question is, did you identify a threshold for the amount of leg raise that appeared protective, or a ratio between trunk position and leg raise? That's
yeah, so these are observations which we're continuing to do. The way it was observed for the purpose of this was leg raise off the ground by over the length of half a foot.
Okay, great, thank you. The next question is from Anne Marie, and she wants to, she's asking, does your research consider older adults with some form of dementia in long-term care homes?
Does the research consider older adults with dementia? Is that the general question?
Yes.
Okay. Yeah, it certainly does. I mean, the population that we are studying, as you may know, is about 70% there's a diagnosis of dementia, whether that's Alzheimer or non-Alzheimer dementia. So the videos that we're collecting, reflect that distribution. We have some measures of, physiologic and cognitive function in older adults that are more high functioning. But in every individual, we have data from the minimal data set. For all, I should say, all of the individuals who consent to, provide us with access to their medical records. So there we have like cognitive performance scale and some other measures of cognitive function. So yeah, I mean, it certainly is a challenge, in terms of fall prevention, injury prevention. I think it speaks all the more to the value of things like compliant flooring and, also issues about championing of hip protectors by long-term care staff, who often, are very influential in making decisions about wear by residents of hip protectors.
Right. Great. So we've got a couple more questions that have come in. So this one is for our third presenter. For the fall dummy experiment, would it be better for it to be dropped from a certain height to mimic the kinematics of a fall rather than sitting and push? That way the initial condition can also be controlled.
Yes, thank you for the question. It's a really good question, actually. And so the videos you've seen are sort of very preliminary pilot tests just to see if we can tip over the dummy. We have been considering a whole host of other systematic ways that we can drop the dummy, including using a harness from a raised height off of the floor, or using maybe an angled rail where we would have significant control over the angle and kind of the initial conditions leading up to a fall. But we've certainly considered that. I think the main limitation testing this by myself right now is that the dummy is very heavy, and that picking it up and dropping it isn't very practical at this point. But we're certainly working on a system to do just that. Thank you.
Great. So question from Mark: considering the overall poor accuracy of existing commercial fall detection technologies, is there one or more preferred solutions you would suggest for use?
I'm laughing because it's a hard question. Well, I think that the main messages that I want to convey is, the limitations that we're dealing with. So that if a provider says, like, I'm going to detect every fall, like I don't want to miss any falls, then you have to understand that you're going to be dealing with some false positives, and you need a method. I suppose it's important for the contact person, like the son or a daughter of an older adult who's using these systems, to just be aware. The companies are certainly aware. Philips invests a huge amount of effort into calling to confirm, and they know that 1 out of 5 of their calls, it'll be a false positive. The other end you can go to is like, I don't want any false positives, so I'm going to move my threshold to get 100% specificity, but then you're going to miss 1 out of 5 falls. So this is where we're at. We're working, and many people are working to improve that accuracy. But I showed you the numbers about just how challenging it is, because you're going to get 1 out of 5. Sorry, you're going to get 1 false positive with like 99.99% specificity. So yeah, I think we'll continue to evolve and build better systems with better algorithms, but we can't pretend that there isn't a big challenge there.
Right. There's no perfect solution yet. Last question that we have here from Sue, 47, so it's for Steve, 47% of falls due to incorrect weight shift. Does your work lead you to think that this may also be the case for community-dwelling older adults?
Yeah, it's a great question, and one that we really can't answer with any definitiveness. I mean, I think that, you know, the sort of general term community dwelling older adult is dangerous, and because it describes such a wide spectrum of individuals, and this is going to become more and more the case as we encourage, you know, and have mechanisms for aging in place, aging at home. There are certainly many older adults living in the community who are nearly as frail as the average older adults in long-term care, in which case there's no reason to believe that the cause and circumstances of falls will be any different. On the other hand, there are those very active, healthy older adults whose the circumstances of falls will be much different, and indeed will be more related to trips and perhaps slips. So yeah, we really need to be careful. You know, that's just one of the limitations of our data set.
Great, thank you. So I don't see any more questions, so I think we can probably end the webinar there. I just put a link to our Age Well webinar series playlist on our YouTube channel, so you can view past webinars there, and you will see this webinar up there in about a week or so. There's a comment saying, thank you, an excellent presentation, and I agree with that comment. Thank you to all three presenters, and have a wonderful rest of your day, everyone.
Thank you.
Thank you.
Bye.
Bye-bye.